Welcome to the fourth lecture on factorial experiment. So, you may recall that in the earlier lecture I considered the setup of a 2 square factorial experiment, and we had found those expression in a very simple way, just from the basic fundamentals. And finally, towards the end I had also shown you that most of the things can be obtained mechanically also. For example, in case if you want to write down the main effect of A or main effect of B or interaction effect of AB, then you simply have to write down either A minus 1 or A plus 1, B minus 1 or B plus 1, and suitably you have to take a divisor also. So, now I will try to extend the same discussion in this lecture to a setup of 2q factorial experiment. 2q factorial experiment means now there are 3 factors. So, those factors can be say capital A, capital B, capital C, and each of the factor is at 2 levels. So, those levels can be denoted by A0, A1, B0, B1, C0, C1, or something like 0, 0, 0, 1, 1, 0 for each of the factor. Right. So, I will try to extend the discussion of 2 square factorial experiment to the setup of 2q factorial experiment. So, let us try to consider this thing now here. And so in case when we have the setup of 2q factorial experiment where we want to conduct the complete factorial experiment, well, I am using here a word complete factorial experiment because we are trying to use all the treatment combinations. So, now I have here 3 factors A, B and here C, and this A is at 2 level, which is denoted by A0, A1, B is at 2 level, which is denoted by B0, B1, and C is also at 2 level, which is denoted by here C0, C1. So, now all together there will be 2 cube number of observations or 2 cube number of treatment combinations. So, I am denoting here n to be here 2 cube, which is equal to here 8. And what are those treatment combination? You can see here I have written here treatment combination, all the treatment combinations over here. You can see here. So, how? You can see here this is my treatment combination 1, this is here 2, this is here 3, this is here 4, this is here 5, this is here 6, this is here 7, and this is here 8. Right. So, now what is the meaning of this A0, B0, E0? That means level of A, B and C, this is at the lower level 0, 0, 0. What is happening in the case of A0, B0, C1? Here I am trying to say that the level of A is at 0 level, level of B is at 0 level, and level of C is at higher level 1. And similarly, if you try to see here in the A treatment combination, everything is at level 1, A, B and C both are at level 1. So, this is how I can write down all the treatment combination, and you can observe here that if I go for higher order factorial experiment, for example, if I try to take here 2 raised power of 4 factorial experiment, then there are going to be 2 into 2 into 2 into 2, which is equal to here 16 treatment combinations. Right. Okay. So, now in case if you try to obtain the observations for each of the treatment combination r times, that means each treatment combination is replicated r times, then in that case the total number of observations is going to be here 2 cube into r, which is equal to 8r. And this 8r observations will constitute the expressions for the main effect of A, B, C and the interaction effect A, B, B, C, A, C and the interaction effect A, B, C. So, one thing, before I go further, so you can see here we have got here 2q factorial experiment. So, there are going to be 3 factors A, B, C. So, now we are going to have here main effects. How many main effects? Which are going to be here A, B and C, 3 main effect, and then interaction effect. They are going to be here A, B, BC, AC, and here ABC. Right, and yeah, obviously there is going to be also general mean effect. So now you can see here that in the case of 2 square factorial experiment, we had to compute A, B and AB along with the general mean effect using 4 observation, but in the case of 2q factorial experiment, I have to estimate the main effect A, B and C, interaction effect A, B, B, C, A, C and A, B, C along with the general mean effect using the linear combination of 8 observations. Okay, so now you can recall that in the earlier lecture I had taken a vector of observation y star which was something like 1, A, B and A B, because we had only here 4 observations. But now obviously here in this case there are going to be 8 observations. So this y star can be extended from 2 square factorial experiment to 2q factorial experiment like this. So I am trying to write down here all the possible labels which are here 1, A, B, A, B, C, A, C, B, C and A, B, C. So this is actually equivalent to saying that when this is the vector of the observation, something like y1, ya, yb, yab and up to here yabc. What is the meaning of this? That is the same as we had used in the case of 2 square factorial experiment. For example, once I am saying here this here ya. So if I try to take here a plot in which I try to give here a linear treatment combination A 1, B 0, C 0, then whatever is the outcome of this plot, which is denoted here by here ya. Right. So and then we had obtained the main effect of A, B and interaction of interaction effect A, B in case of 2 square factorial experiment as a linear functions of these y's. So we had denoted earlier L transpose something here y, where L was the vector of all the elements unity, that is 1 with different positions of +1 and -1. So similarly here in this case, when you want to estimate either of this effect A, B, C, A, B, B, C, A, C or A, B, C, what we have to do? All these effects, they can be estimated by L transpose here y, a linear function of these 8 observations on y. The only thing here is that this L is going to be changed. For A, this I am going to denote here as a LA, for B I am going to denote here as a LB prime and so on. So all these effects, main effect and interaction effect, they can be estimated using this linear function. And if you recall that in the 2 square factorial experiment, I had constructed a table like this one, what you can see on the screen. Now I am trying to extend it to a 2q factorial experiment also. One thing what you have to see here, that by this table how I would try to obtain a particular effect. For example, if I trace, say suppose I want to estimate here the interaction effect BC. So BC can be that 1 over here, some here divisor, and then this will be your here y1, now this here plus ya minus yb, this minus yab minus here yc plus here yac plus here ybc plus here yabc. Right. So that is the advantage of this table. So this table has been constructed exactly on the same lines what we had done in the earlier case. Beside those things, there is one more feature which you have to observe here. If you try to look on this highlighted part, which I am going to denote here 1 A B and here A B. This is the same table which you had obtained in the earlier lecture in the case of 2 square factorial experiment, right. And in order to create this table, you need not to write from the scratch all the expressions of y a, y b, y c, etc., or say a b, etc., but I will try to show you that how you can construct this table directly after writing some of the rows or columns, right. So, you can see here, suppose I try to consider the column corresponding to here A, right. And so, if you try to see here, I will try to use here a green color pen, you can see here this column, right. This A here has here plus sign, this B here is here minus sign. So, now in case if I want to obtain here A B, so A B can be expressed here as say A into B. So, I can find out the sign of this A B just by multiplying the sign of A and sign of B. So, sign of A here is here plus and sign of B here is say here minus 1. So, this is going to be here minus 1 and this minus 1 comes over here, right. Now, similarly in case if I want to find out the sign of here A B C in this column here A. So, A B C can be written in several ways. For example, this can be written as A into B into C. So, the sign of A B C can be determined by sign of A into sign of B into sign of C, which is here, which you can see here, which I am now going to denote. Highlight with red color A, B and here C. This is plus minus minus, which is here plus 1 into minus 1 into minus 1, which is equal to here plus 1, and this one is appearing here. Also, there are other ways also. Sign of A B C can also be obtained as here sign of A B into sign of C. So, sign of A B you can see here with my pen here with this here, this is here minus. So, minus 1 into sign of C, which is here minus 1. So, which is equal to here plus 1. So, this is how we can obtain different types of signs from this table, and that is the advantage of creating such a table, that once you create some of the rows and columns, the other can be obtained by the simple multiplication of other symbols. The first row here is for the general mean effect that you can see here, which I am denoting highlighting here in this blue color. So, this is for here I. So, this I can be expressed by here, see here 1 times here y star, where 1 here is something like a column vector whose all elements are 1, right. So, when we are trying to multiply any of the symbol, this plus 1 or say minus 1 with plus 1, the symbol will remain as the same, right. So, that is what we say, that if other rows are multiplied with the first row, they will stay unchanged, and therefore, we call this first row as a identity relation, right. So, all other rows except identity rows, they will have plus signs as well as minus signs, whereas this identity row will always have only the plus sign, right. And yes, now we have understood that if I try to replace the plus sign by plus 1 and minus sign by minus 1, then we can obtain the vectors of orthogonal contrast that I already have shown you, right. Okay. Now, what you have to understand here more, that once I am trying to multiply the signs of here A and B, I will get here AB, and once I try to multiply AB by here B, mathematically it will become here something like A B square, which is equal to here going to be here 1, right. This is what you have to consider. All the squares are just going to be taken here as a identity relation. So, for example, if I try to multiply here AC into BC, this is going to be A into C square into B into B. So, this becomes here A C square B square. Oh, sorry, this will be here, this won't be here, this is here A C square B. So, this C square becomes here I, and we get here AB, right. So, this type of structure will help us in estimating the average effect. How? For example, if you try to see that the expression for estimating the main effect of A, it is coming here like this. Now, the question comes, how does this expression is coming into picture? Well, if you recall that in the earlier lectures where I had considered the 2 square factorial experiment, there I had shown you that how we were computing the main effect of A and main effect of B by taking the average effect of some combinations. Since I was considering the 2 square factorial experiment, so that required a smaller space, and I could show you all the algebra on the screen very clearly. But now, since I am going with 2q factorial experiment, and then if you go for higher order factorial experiment, showing all those expressions on the screen becomes difficult. So, but for these things, when I am trying to compute the main effect of A using the 2q factorial experiment, I can say here that that first I try to find out the average effect of A at lower level of B and C, which is obtained here like this, and that is what we are indicating using our standard terminology by here A minus 1 upon here R, and similarly then we try to find out the average effect of A at lower level of B and lower level of C, actually both. Wait, here there should be a correction, this is actually higher level of B and lower level of C. So, this becomes here like this A1 B1 C0 minus A0 B1 C0, and which I can write down here like this. And similarly, there are two more things what I am going to consider here, that I am trying to consider the average effect of A at lower level of B and higher level of C. So, this will become here lower level of B, that means B0 B0, and higher level of C, that is C1 and C1. So, this I can denote by this expression AC minus C upon R, and finally, I also try to find out the average effect of A at higher level of, sorry, there is a typographical mistake, higher level of B and C. So, this becomes here see here B and C both are at the level 1. So, now this can be expression this can be expressed as ABC minus BC upon here R. So, now you can see here that the average effect of A is being measured by 4 quantities. What are those 4 quantities? First quantity, second quantity, third quantity, and here fourth quantity. And now I am trying to find out the average of all those 4 quantities in first, second, third and fourth aspect, and this will give us the value of this here main effect of A. So, you can see here that as soon as I am going from 2 square to 2 cube, the things are becoming little bit difficult, and means it is difficult for me to explain all the things as neatly as I could do in the case of 2 square factorial experiment. But now using the same thing here, this expression means A is equal to this expression which is here, I can write down the main effect of B, C and the interaction effect A B, B C and A B C directly. How? Now, you can see here, I will try to use here a different color of pen, say red, using the same type of concept which I introduced in the earlier lecture. I can write down here this A here as a A1, because there are 3 factors. So, I have to write down here A1, B1, C1, and now I have to write down here the divisor, whatever is this, and then now this A is coming here as a. So, I will try to write down here A minus 1. Now, there is no B nor is no C. So, I will try to introduce here plus 1 and plus 1, and if you try to open it here, you will get the same thing which is written here, and divisor here is 4R. Right. Now, using the same concept here, I can also write the main effect of here B and C like this. B is here. So, I can write down here this minus sign here with this here B corresponding to this B, and then I will write down here plus 1 and plus 1 with A and C, and the divisor is going to be here 4R. Right. And similarly, you can see here for the C, I am trying to use here the minus sign in the C minus 1, and then I am trying to use A and B with the plus signs over here. And similarly, when I am trying to consider here A B, then I can, so there are 2 letters A and B which are common here. So, I will try to denote here both the things by minus 1, and there is no C here. So, I am trying to use here the plus 1 sign. Similarly, for this here AC also there are 2 common letters A and C. So, A is here positive and negative, and C here is with minus 1, and B will come here as say plus 1. And similarly, when you come to ABC, all the things are coming, all the 3 letters A, B, C are common. So, and C we are going to get here minus 1. Right. So, this is how I can write down all the expressions for A, B, C, A, B, B, C, A, C and A, B, C. And you can see here that all these interaction effect as well as main effect, they have been obtained using the different combination of the 8 observations on Y's, which are related to the treatment combination 1 A B C A B B C A C and A B C. So, that is the beauty of this factorial experiment. And here if you, although I am not writing here, but if you want to have here the general mean effect, which is straightforward. Now, general mean effect is going to be based on 8 observations. So, I will have the divisor here 1 upon 8, and every suppose every observation is repeated r times. So, this will become 8r, and then now here I have to give here all the treatment combination with plus sign 1 plus A plus B plus C plus AB plus BC plus AC plus ABC, which is straightforward. Right. And now, after this, in case if you want to write down the corresponding sum of squares, so that rule we have understood in the earlier lecture, that it is given by L transpose y whole square divided by the total number of observation, which is here R into L transpose L, and each of the sum of squares under the normality of y, we will follow a chi-square distribution with 1 degrees of freedom. Right. And based on that, I can find out the mean squares due to any effect just by having the sum of squares due to the effect divided by the degrees of freedom, and based on that I can find out the F statistics, which is the mean squares due to any given effect divided by the MS E, that is the mean square due to error, and this will follow a F distribution, and we know that each of the degrees of freedom is of sum of square is 1, and whatever is the degrees of freedom of error, that will come over here. So, based on that I can say that the decision rule is that we try to reject the corresponding null hypothesis at alpha level of significance whenever this calculated F is greater than the tabulated F which is obtained here. So, these are pretty straightforward thing, and all these calculations they can be arranged in the ANOVA table, where there are 8 sources A, B, C, A, B, B, C, A, C and A, B, C here. But if you try to observe here one thing which I will try to take up in the next lecture, that I am trying to write down all these all these factors in a particular order. First I am trying to write down A, B in the alphabetical order, and then I am trying to take its interaction, and then I am trying to take here C, and then I am trying to multiply this C with here A, with B and with A B, and I am writing here C into A C, C into B B C, C into A B, that is A B C, and then corresponding sum of squares SSA, SSB, SSAB, SSC, SSAC, SSBC, SSABC, SS error, they are obtained here, and then they have the degrees of freedom here 1. Each sum of squares follows a chi-square distribution with 1 degree of freedom, and from there we try to obtain the mean squares due to A, B, C, A, C, B, C, A, B, C and error, and based on that we try to obtain the F statistics for each of the main effect and each of the interaction effect of 2 factors and 3 factor. So, this is how we can conduct the 2q factorial experiment. Now, if you try to see, I have taken the example of 2 square factorial experiment, and then I have taken the example of 2q factorial experiment. My idea was not really to teach you 2 square or 2q factorial experiment. My objective was that how different terms are coming into existence. Those terms have been obtained on the basis of data set using the statistical theory, and I wanted to demonstrate how this statistical theory is being used here to construct this ANOVA table. Means how the same set of observations are used in different ways to obtain the main effects and to obtain different types of interaction effect. You have to observe here that we have got here only 8 observations. Just those 8 observations have been combined in different ways using only addition and subtraction to find out the main effect of A, main effect of B, main effect of C, then interaction effect A B, B C, A C, and the interaction effect A B C. And then they have been obtained in the form of a linear contrast. You can verify here that all the expressions of L star y or say L transpose y star, whatever we have obtained, they are the linear contrast estimable. So, all the parameters can be estimated, then we can obtain the sum of squares. Using those sum of squares we can obtain the mean squares, then from mean squares we can obtain the F statistics for the test of hypothesis. Now, if you try to observe here one thing more, earlier when you were trying to use RBD, then there were only 2 F statistics, one was for the treatment effects and one was for the block effects. And what was happening? That all those treatment effects, they were combined in a single basket. For example, if I try to take a 2 square factorial experiment and if I try to conduct it inside the randomized block design, then there were 4 treatment effects A, B, AB and general mean effect. And similarly, in the case of 2q factorial experiment, we had 8 treatment effects A, B, C, A, B, B, C, A, C and A, B, C along with the general mean effect. Earlier you were trying to test the equality of all the treatment effects under the same hypothesis, but now you have got 3 F statistics for the 2 square factorial experiment, y 3, one for A, one for B and one for A B, and you have got 7 F statistics in the case of 2q factorial experiment. For what? For testing for the treatment effect A, B, C, A B, B C, A C and finally A B C. So, now these factorial experiments are giving you a liberty that you can test the hypothesis for the individual factors as well as their interaction effect. And that is the advantage of the factorial experiment, that here we can conduct such type of test of hypothesis. So, in the next lecture I will continue with the factorial experiment in some more detail, and till then you take care and see you in the next lecture. Goodbye.